Welcome everybody to another session from Narrow Research. I'm Srijit here, and in this session we will be focusing on energy decomposition analysis. Speaking about energy decomposition analysis, it will cover the theory in plain terms how ADF implements EDA, step-by-step practical instructions, and how to interpret results, common pitfalls, and useful tips for our analysis. So speaking about EDA, what is actually energy decomposition analysis? What is the purpose of this methodology in research and development? So EDA breaks the interaction energy between molecular fragments into physically meaningful components. The typical components which is used in ADF are electrostatic interaction, which is represented as delta E electrostat, which is actually classical Coulomb interaction between fragment charge densities. Then of course Pauli's repulsion or exchange repulsion, which is actually the destabilization from anti-symmetrization or the overlap of occupied orbitals. And then comes orbital interactions or charge transfer or polarization, which could be known as the stabilizing energy from orbital mixing, charge transfer, and polarization when fragments form the complex. And comes dispersion, which is known as London dispersion correction. So the total energy interaction energy could be the sum of electrostatic interaction, Pauli's repulsion, orbital interaction, and this dispersion correction. So how this thing can be implemented in ADF, or how ADF implements EDA? What are the key points? So ADF performs, or this module performs EDA by computing the energies of separated fragments with their densities frozen or prepared and the assembled complex. So the method isolates contributions by building the complex in steps. So how to add electrostatics, anti-symmetrized polys, and then allowed orbital relaxation. So ADF support fragment definitions, for example, molecule A, molecule B, different choices of references, states, for example, spin state, charge, and frozen density or relaxed treatments. So we can obtain a further decomposition of the orbital interaction into pairwise orbital contributions or symmetry adapted components in many cases. So when to use EDA? So actually understanding the nature of non-covalent interactions like hydrogen bonding, halogen bonding, pi-pi stacking, metal ligand bonding analysis, ligand design, comparing bonding in different geometries or substituents, and rationalizing reaction barriers. For example, how to compare the interaction components in transition states versus the reactants. So speaking about the practical workflow, preparing the structure, for example, a geometry optimized, preferably at the same level of theory when we are using ADA, for the full complex of fragments as appropriate. Decide which are the fragments, for example, how to choose chemically meaningful fragmentation, for example, ligand versus metal center or donor versus acceptor. Make sure fragment charges and spin states are consistent and physically sensible. For example, we need to choose the method or basis of settings, select functionals, for example, correlation function like GGA or hybrid. Then for heavy elements, SORA, and even basis set, the TZP is a common choice, and dispersion correction if you want dispersion correlation. So while running the EDA calculation in ADF with the fragment definitions, ADF will output component energies. And for the further analysis, we can compare magnitudes and signs, look at orbital contributions, and if needed, this natural orbitals for chemical valence analysis to map charge transfer channels. So these are actually the intro about EDA. And in the next coming sessions, we will be focusing more into these examples, which is available from our SCM web. So EDA with restricted fragments, unrestricted fragments, and also natural orbitals for chemical valence. So these are the things which we will be focusing in the coming, discussions. Thank you.